Okay, so now we're going to spend just about 10 minutes talking about topic 4.4, and that is diffraction and interference. So, diffraction, we'll start off with that. We've already talked a decent amount about interference, but diffraction is a little bit different. It's when a wave goes around a barrier or through an obstacle. Well, I sort of said that weird, but imagine if light was coming up to so here's well, let's not do it that way. Let's do it this way. So we have these wave fronts of light, sort of like Huygens principle again, just with the little wavelets, and they come up and they hit a brick wall, right on the corner there. So we know that behind here on a screen or something, we would get a shadow back here. Well, and diffraction, so because we know that part of it was blocked, so that means that this blocked the light from going around, and we sort of got a nice distinct shadow right here. That was bright, but then this was all shadow here. I'll write that in there as best I can, and what happens is that diffraction takes place when the wavelength is comparable to or bigger than the size of the opening or to the obstacle. And in this case, it was, so you really didn't get much diffraction, so it didn't go around it. Now think about that. Light has a very, very short wavelength, so it has to be comparable to or bigger than the obstacle or the opening. But think about sound. Sound, on the other hand, has a very long wavelength in general, on the order of meters it can be, or close to, and then it gets quite short when you get up to 20,000 hertz or so. But still, sound has the ability to go around much bigger barriers, so you tend to hear something if someone's in another room or something, although there's a lot of echo and reflection taking place there as well. So let's continue this talk of diffraction. So remember this, the spreading of a wave through an opening or past an obstacle, that's diffraction. Make sure you get that down. And you get significant amounts of diffraction when the wavelength is equal to, I guess, or close to, or bigger than the size of the opening. You'll get significant amounts. So what I mean by that is that if you had, here's a barrier and here's a barrier, and then you have wavelengths approaching this barrier. Well, if this opening right here is comparable to the wavelength, remember that from here to here is the wavelength, then you're going to get significant diffraction. So this comes through, and you would basically, as it approached it, so let's just assume that this wave set is approaching it, then we know that all these waves along here that hit here would be blocked completely, but the ones that came through here would come through, and you'd get the waves passing through. And but if you think of Huygens' principle, they're not just going to pass through like that. You would get, remember, it went around the barrier. So how is it, when Huygens was talking about these little wavelets forming and reproducing themselves continuously, then you would actually get it coming through, especially if you imagine one particle coming through. Not so bright back here, sort of dull behind it, but if you put a screen up here, you would get a bright spot in the center, which we'd expect, and then it would sort of get dimmer as you go away. And then we'll talk a little bit about the interference that's going to take place here shortly on this screen a little bit later. So anyway, so it wouldn't. So just to follow up with that. So as the wave, since these waves, the wavelength lambda was approximately the same as the opening, then you got a significant amount of diffraction taking place. And remember, that means that it went around or through the barrier. And so anyway, we'll continue our talk with this and you can sort of, we'll see more of this as we do our little investigations in the class where we can look and use diffraction grating to discover the wavelength of a typical neon laser, Heine laser, in the classroom. And also just some applications of diffraction. One of them was when I was a young kid in college, we actually got to do a interesting little lab on X-ray diffraction, and where we looked and identified crystals by looking at shooting crystals, X-rays through the crystalline structure. Now think about that. Crystalline structures have openings in them where the crystal forms its little faces and the lattice structure. There's openings between the atoms that form the crystal, and those openings, if they remember now, if the wave approaches the distance between the opening from one atom to another, then you can get significant diffraction taking place. And someone realized this a long time ago, and they started shooting X-rays, which have very, very, very small wavelengths that X-rays do. And by shooting them at crystals, they're actually able to get the X-rays to diffract, from that diffraction pattern from each crystal, you can actually do an identification of the types of crystals just from the diffraction pattern that forms as the wave goes through the crystal, and as it goes through it, goes around the barrier that the crystal structure creates, and creates a new pattern on a photographic plate, and you could look at that structure and identify the mineral. So that's where we'll stop with this one, just the talking of diffraction. That'll give you some introduction, and then along with you reading through the concept of diffraction, you should be okay for tomorrow. Okay? All right.